Okay, so last but not least, we have Andreas Bastian. He's going to be telling you about 3D printing via laser sintering, thermoplastic powders. So Andreas finished his BS last year from Swarthmore in engineering, and over the last year he has been leading R&D at MakerBot, so one of the leading open source 3D printing companies that started a couple years ago, and is 23.
All right, good, thanks. So again, I'm Andreas Bastian. I'll be telling you guys about laser sintering, 3D printing via laser sintering and thermoplastic powders. So I've, for a very long time, been very interested in tools, tool making, and the processes by which tools manipulate materials. So this has been kind of a very fundamentally human thing. We develop tools when we have a specific problem that we need to tackle. So it started very simply, like we literally couldn't tackle envelopes, so we needed like spears, stone tools, things like that. And it progressed as society progressed, as we developed agricultural technologies, went through the Industrial Revolution, and now we find ourselves in a digital age. And with that, a lot of new tools have emerged, and one of the most interesting, I think, are these additive manufacturing 3D printing technologies. So what's very special about these technologies is they work in kind of a reverse manner of all previous manufacturing technologies. They actually put material down where you want it to be, which is this kind of very unique inversion of how it's been done previously. So what this allows for is the kind of a decoupling of complexity from difficulty in manufacturing. So you can make this little 20-legged automaton with literally hundreds of moving parts with one machine, with one material in an afternoon. So it's a very impressive technology that really removes a lot of boundaries from design, from human design, that have been kind of ingrained in our design processes for literally millennia. So again, the machine doesn't care how complex the object is. It can make something with a kind of a static complexity, like this form, with the same degree of ease as it could make the previous form with all those tricky moving parts. So the process itself, though it is very capable, it has kind of pretty humble beginnings. So you can think of it like making crème brulee, in which you take a custard, and you spread a thin layer of sugar on top, and then you melt that sugar with a torch. If you were to use a smaller torch and just melt small regions of that sugar design, making an image, a drawing of that sugar, you would just get one region of solid material. If you were to add another layer of sugar on top of that and melt that layer, you'd start to build up an object. So in practice, in a 3D printed machine, this is a machine I built a couple years ago in college that laser sinters wax powder. Your laser moves around, traces out, and fills in each cross-section of the object. And so you see here, we're making a gear. The rest of the machine is kind of its sole function is to queue up layers of powder for the next layer for the laser to melt. So when you're done with that, you get a complete solid object, which you can, in this case, use for lost wax casting. So you can see here, just for scale, what that gear was like. So we know how to make gears, but we don't know how to make the far more complex structures like this liver vasculature. We just haven't had tools that can approach a structure of that complexity before. But we're starting to see people exploring similar structures using this laser sintering 3D printing technology. So this is actually a lampshade that a design firm in Boston came up with. So we need some sort of a laser sintering machine to tackle this research. So this is the machine that I built in college. It's not exactly the most structurally sound or user-friendly. It had some, as you can see in the gear, that you could make small parts. There were some challenges with spatial resolution, and this is also dramatically accelerated. So we were interested in finding some sort of piece of commercial hardware that we could repurpose that would address the problems in the previous prototype and would be something that you could just buy and would be kind of more accessible for, as a development platform. So we found that laser cutters actually address most of the problems with that first prototype. They're much faster, they have a much higher power laser, and they're very precise in terms of their positioning system. However, the positioning system is only two-dimensional, so you still need some additional hardware to break into 3D. So I spent the past couple weeks developing a piece of hardware that just manages the powder and that third degree of freedom, that third axis, that lets you break into three-dimensional objects. So it's very simple. There are two pistons that just manage a bed of your print bed of powder, and a device for distributing that powder. So this is what the hardware looks like, actually laser cut and assembled. It's just laser cut parts and 3D printed parts. This is just an example of one of the sub-mechanisms. This is a little counter-rotating roller that distributes powder from the reservoir piston to the print piston in thin layers, thin sequential layers. And when you lay out a nice bed of powder, so this is some isomalt powder that we ball milled upstairs, you can then use the laser to trace out patterns. So we're starting very simple to just establish the very basic parameters for sintering. So this is just a speed and power traversal. Each line of this speed. And so we're starting to get close to sintering parameters. We're getting things, sintered regions on the millimeter scale, which is promising. So once we can do 1D, it's a short step to 2D, and once we do 2D, it's another short step to 3D. So AMRI has been a very unique place to conduct research like this. A lot of the kind of practical aspects of this project are very firmly footed in a lot of the open source infrastructure around, available in both the open source software and open source hardware communities. So all the electronics are open source 3D printer based electronics. The software as well is open source 3D printing software. And what's really unique here is that we can take a lot of this like hardware development, process development, infrastructure, and then quantify it with all of the, the amazing academic resources that are normally not available to hardware development projects like this. So you can see we've done a little bit of characterization of the laser power, and we've also done some imaging of these small sintered structures. So we're going to try to move forward with this using laser sintering as a way to create these very complex structures, these very complex vascular structures, and merge this with Jordan's research in hydrogel casting of these sugar lattices to make vascular networks. So with that, you can find more of the kind of current documentation of this project on OpenSLS.tumblr.com. Feel free to contact me too with any questions, and I can also take questions.
So I know in Jordan's previous work, you would use sugar and coat hydrogel and then melt away the sugar. So would your laser sintering technology be compatible with that? Because it seems like the material, the final product doesn't seem dissolvable. I guess.
The final product will be dissolvable because we're actually going to be sintering sugars. So we're using just very finely ground sugar glasses. So the same material that Jordan's worked with in the past, but we're fusing it and forming it in a new way. So it should be compatible with the hydrogel casting process.
So what does the laser sintering give you that the melt extrusion did?
So one of the really amazing things about the laser sintering is that makes it a very different technology from the melt extrusion and some of the other 3D printing technologies is there's still this issue of material support. So when you extrude material out, it's like a spider making a web, that extrusion, that filament will droop under gravity. And so you do have to factor gravity into your design. So you don't quite have unlimited design capability with a lot of the extrusion-based technologies. But with the laser sintering technologies, because every layer is kind of perfectly supported by the material underneath it, you really have a tremendous amount of freedom in the geometries that you can craft with that. So you can create very dramatic overhangs and pieces free floating in space. So it's much less constrained. So you should be able to make far more intricate and complex structures this way.
So with the designs you're currently making, they're just kind of straight lines. It's easy to model with like an equation, but for the vasculature, when you're making your file to print, do you foresee modeling that with equations in your software, or taking like a sliced CAD file or something instead?
Yeah, that's a good question. I mean, they're kind of, one of the funny things is we don't really have design tools for complex geometries like that that are kind of, that don't have any right angles, things like that. So one of the things Jordan's interested in doing is actually taking scan data and converting that to a mesh that can then be processed by the software that runs these 3D printers.
Couldn't you use Wolfram's autonoma methodology to create some really cool little fingers?
Could create very cool fingers, but I don't know. I'd have to take a closer look at that and see. I think we are just beginning to understand a lot of the kind of subtle forces that led to this geometry. So I feel like we should probably take our cue from systems like this first before trying to synthesize commands.
Okay, let's thank Andreas and congratulate him. Now, I just want to emphasize again, this is an experiment, this is a pilot this year. We're trying to see how it'll work, what we can do better. So we would love your feedback. We need your feedback to make this better. So keep apprised of the project. And if anyone wants to see sort of the lab where all this has been done, we can do lab tours now for anyone interested. So thanks again.